break, so I forgot. Fine. Yeah. So I hope this point is clear now, right? So when I say reduce the expression, bring it into its minimal form, I mean to say that you have to find the expression or simplify that expression in such a way that the expression is cannot be further reduced, and at the same time it should have minimal number of product terms with minimum number of literals in it, or minimum number of sum terms with minimum number of literals in it. Okay, so that number of component requirement or hardware requirement will reduce, which will reduce the cost of implementation of the same function, right? So in the last class, I had been I had been taking different Boolean algebra laws and theorems, and we have seen how to apply those Boolean algebra theorems in order to simplify the logical expression. Okay. So whenever we have to simplify the Boolean expression by using Boolean algebra, what we have seen is that we need a better understanding of Boolean laws and theorems, right? And during the process of simplification, we have to predict each successive step. In the last class, I had taken several examples where we were simplifying the logical expressions using Boolean algebra theorem, right? And what you observed, we saw that when we are simplifying the Boolean expression, we have to predict one step ahead. We have to think one step ahead. We have to predict each successive step, and sometimes we may not even get unique simplified expressions out of it. Okay, so let me take an example to show you this, and then I'll tell you the conclusion, what we conclude from all these things, right? So let us take an example. Let's say you have an expression. So let's say we have a 3-variable function f, and expression is, let's say, in the form of min-term list, which includes 0, 2, 3, 4, 5, 7. So let us just refresh first. We'll simplify this expression using Boolean algebra theorem, and then we'll look at drawback of this method. Okay. So can you solve this? Can you people try this out? I'll give you 2 minutes of time to do it. This is the logical expression. Expression is given in terms of min-term list, which includes min-term 0, 2, 3, 4, 5, 7. So the first step would be, we will write the expression in terms of product terms. So 0 means A bar or A bar, B bar, C bar plus 2. So 2 means A bar, B, C bar. 0, 1, 0. Then 3 is 0, 1, 1. A bar, B, C. Then 4 is 1, 0, 0. A, B bar, C bar plus 5. So 5 is 1, 0, 1. So A, B bar, C, and then last is 7. So A, B, C. Okay. Now you simplify this. Let me know what you people are getting as a simplified expression. Simplify this expression using Boolean algebra theorem. I hope this is clear how I have written this, right? This corresponds to 0, 0, 0. It means min term 0. Second min term is 0, 1, 0. So that is 2. Then 0, 1, 1, which means 3. 1, 0, 0, which means 4. 1, 0, 1 is 5. And 1, 1, 1 is 7. I suppose there is no doubt in this, right? Okay. Now you simplify it. Everyone doing? Anybody got?
Ma'am, I'm getting A bar dot C bar plus A dot B bar plus B dot C.
Plus A bar, will you please repeat?
A
A
bar
bar B
dot C
plus,
bar,
uh,
A bar C bar plus AB bar plus BC.
3 terms, right?
Yes, ma'am.
Okay. Any other? Everybody got same?
Yes, ma'am.
Yes, ma'am.
Everybody is getting same result, right? Okay, let me also solve this here. Okay, let me solve this. Suppose we take first 2 pairs, okay, and then let's say I'll take this 100 and 101, these 2 pairs. Okay, so what you get, if you take these 2 pairs, you can combine, apply combining theorem. So what you get, or distributive theorem also, A bar, C bar is common. What you get inside is B plus B bar. If you combine these two, what you get, A B bar as common, and then inside you have C bar plus C, and then you combine the remaining two, what you get is BC as common and A bar plus A inside, right? So which means A bar C bar plus A B bar plus BC. B plus B bar, logical sum of B and B bar will give you 1, right? Similarly, C bar OR with C is 1, A bar OR with A is 1, right? So you get this kind of, this is what you people said? This is the
Yes,
solution
ma'am.
that you got?
Yes, ma'am.
Yes.
Yes.
Is there anyone who got something else? Any other expression? Is there anyone who got something else? Okay. Let me now redo the same question. Okay. I'll again simplify this. Expression was A bar B bar C bar plus A bar B C bar plus A bar B C plus A B bar C bar plus A B bar C plus A B C, right? This is the expression. So let me now, let's say I'll combine these two. I'll make pair of these two, then I'll make pair of, let's say these two, and then pair of these two. Okay. So I decide to make pair in this way. Okay. So the first 2 terms, if I combine them, what you get is A bar is common, C bar is common. So you get A bar, C bar. C bar OR with B will give you 1. Okay. Then if you combine these 2 terms, what do you get? What is common in this? There is nothing common, right? So it will be A bar BC plus A B bar C bar. Then if I combine these two, you get AC and then B bar plus B, right? So what we get is A bar C bar plus A bar BC plus A B bar C bar plus AC, right? Let us further reduce this. So if I take A bar common, okay, so you get C bar plus BC plus, if I take A common here, you get C plus B bar C bar. So let us apply distributive law now. What you get is A bar. This becomes, if you apply distributive law, what do you get? this term will split into two, C bar plus C and C bar plus B, right? Dual of distributive law. So C bar, you get two terms, C bar plus C dot C bar odd with B, right? But we know that C bar dot C is 1. So actually, we could have written directly this, okay? But anyway, I'll show you all the steps. So B bar plus C and C plus C bar, right? So this becomes A bar C bar plus B plus A B bar plus C, right? So if you open this, you get A bar C bar plus A bar B plus A B bar plus AC. Can you further reduce this expression? Is it possible to reduce this last expression? Look at the last expression now. What we have got is A bar C bar plus A bar B plus A B bar plus AC. Can we further reduce it?
We can use the consensus theorem, right?
नहीं, consensus theorem use करके हो रहा है? No. This is the reduced. This is in reduced form. We cannot further reduce it. Okay. We cannot further reduce it. This is in the reduced form. But is this the minimal expression? Is this the minimal expression? This is not the minimal expression. You see this, the earlier one, when we solved it earlier, we got this as a reduced expression, right? This was the expression that we had obtained. And now when I change the pair, okay, I have got this expression as a reduced expression, okay? Although both the expressions are in reduced form, we cannot further reduce either this expression or this expression, but then the later one is not the minimal expression, okay? The former one, this one, is the minimal expression, okay? So you see, there is no fixed procedure as such, okay? When you use Boolean algebra theorem to minimize the logical expression, there is no fixed procedure. You can, it is up to the user, up to me, which pair I want to combine, right? But I have to think one step ahead. Okay, if I combine this, will I be able to then apply any other theorem to reduce it further? So that thought process has to be there in the mind all the time. Okay, so that thought process has to be there, isn't it? And so somebody may get this as a final expression, somebody may get this as an expression. Although this expression is also in the reduced form, this cannot be further reduced, but this I cannot call it as a minimal expression. So if you solve this and write this as an answer, you will get no marks. This is not the minimal expression. This is not minimal expression. Okay? Because we know that if we would have paired the terms how we did in the earlier case, we would have got the expression which will require lesser number of components to realize it, right? Because there is one term less. You see, as I said, minimal expression means the expression that will have minimum number of product terms with minimal number of literals in each product term. So if you compare the two functions, output functions, okay, the first one is the minimal one, right? Second one has one additional product term. So this is not the minimized expression for the, although this is the reduced expression, we have reduced it and you compare it with the original expression, but this is not in the minimal form, okay? Similarly, if you decide to take some other pair, okay, there can be even more combinations, okay? Suppose I decide to, yeah. Yes.
Taking B bar C bar common, we'll get A plus A bar.
Where you are saying?
In the same expression, like the first and the fourth. In the first and the fourth,
that's what I'm saying.
C bar is
this
common.
Expression, this original expression you are saying, right?
Yes, ma'am.
Yeah. So there is one more angle to it. You can combine first and last term first, not first and last, first and third term first, then second and fourth term, and the left out term. Okay. So there can be lots of choices, isn't it? There can be other combinations also, which may also give you the reduced form. which is obviously going to lead to some expression which will be not, which will not be able to, which you won't be able to reduce it further, right? So with different combination, you get different output. Okay. So there is no fixed way, fixed procedure to go, to proceed with this kind of technique, this technique. Okay. So I suppose you are getting my point. Why I have taken this example. Okay. So there are, see, the drawback of this mechanism, this technique, is that we have to predict each successive step during the simplification process. This is the first drawback. Second thing is that the simplified expression may be in the form that cannot be further reduced, but not necessarily a minimal function. Okay? So the expression that you get, it may be in the form which cannot be further reduced, but it may not. It is not necessary that it would be the minimal expression. Okay. The reduced. Third thing is that the reduced procedure is not unique. Okay? So application of different theorems may give different reduced expressions. So there is no fixed, reduction procedure as such. Somebody may use some other theorem. I have just used distributive theorem and solved it. Somebody may use some other theorem and may reach to some other reduced expression, right? And next is that another point is that there may be more than one solution. There may be more than one solution. In fact, when I said you can combine different pair, you will find this expression. Basically, this expression has two solutions. Okay, this is one solution, and if you pair it in some other way, you will get one more solution to this function. Okay, you can try it out. You take some other combination. Okay, and you will find that you will get one more solution to the same function. Okay, so there are two minimal solutions basically for this expression. So what I mean to say is that, you see, this method is not that reliable. Okay, see, you try it out. Combine first and combine first term and let's say third term. Okay, then you combine second term with third term, and then you combine last two terms. Okay, what is the minimal expression? What is the expression that you get?
Ma'am, I've done in another way, but I've got a different answer.
So you can, you may get some other answer also. What is the answer? How many terms are there in that?
4 terms.
4 terms, right? So that is again not a minimal expression. But if you do it like this, the way I have shown here, first term, combine it with third term, fourth term. First and fourth, what do you get? Let me just change the color of pen and I'll write it here. Okay, if you combine, can you see this marking? I have made some marking.
Yes, ma'am. Yes, ma'am.
See, first term and fourth term, I'm combining them. So what you will get? What is common? B bar, C bar, right? So you get B bar, C bar plus second term combined with third term. What do you get? A bar, B, right? And third, last two terms, if you combine, you get AC. This is again a minimized expression, isn't it? This again includes three terms, three product terms. Okay. So these are this or this. Both the solutions are correct. If you try to implement any of these two solutions, any of these two expressions, they will require equal number of hardware, basically. Okay? That's why I'm saying both are minimal solutions. So there are two solutions to this sum. Okay. But this one, this third expression, this expression that we obtained, this is not the minimal expression. Okay. Although it is in irreducible form, but this is not the minimal expression. Okay. So if you go by this Boolean, if you apply Boolean algebra theorem and try to minimize the expression, you will never be certain that whatever you have, whatever simplified expression you have obtained, whether it is really a minimal expression or not, right? There is no certainty because you don't know. You have applied some theorems and you have reached to some irreducible form of function, which may or may not be the minimal function. So there is no surety, there is no way to confirm it basically, right? Otherwise, you'll have to work out with all different combinations, different possibilities, different theorems, and it will become very, very tedious, right? So what we require is we want some kind of some kind of systematic procedure so that it will tell, it will confirm, it will give the certainty that this is the minimal expression, this is the solution for this function, minimize expression. Okay. Also, the procedure should be in such a way that it should also reflect all the all the possible solutions. Now with this method, I had to show you, if you do it like this, you get another minimal expression, right? So it may not click to any others. It is not necessary everyone will come to know that there is one more solution to this, I should try it out, right? So there has to be some procedure that will, that will show you all the possible minimal expressions easily. Okay, so you know how many solutions are there for a given logical function, right? So one of such methods is called Carnot method, which I'm going to explain now. I hope you have understood drawback of this minimizing the logical expression using Boolean algebra theorem. Let me again repeat disadvantages. Drawback of simplifying the logical expression using Boolean algebra theorem is that, first of all, you have to predict each successive step during the simplification process. You have to think one step ahead. Okay, while you are during the simplification process, you have to think one step ahead. Okay. Second problem is that the simplified expression may be the simplified expression may be in the irreducible form, but it may not be necessarily a minimal function. So there is no certainty that whatever simplified expression that you obtain is the minimal expression or not. Okay. Third drawback is that the reduction procedure is not unique. Somebody may use some theorem, someone else will apply some other theorem to reduce the function. So there is no, reduction procedure. I mean, there is no fixed reduction procedure as such. So the reduction procedure is not unique. So application of different theorems, it can result into different reduced expressions. Okay, and one more drawback I said, what was it? That there can be more than one solution for the given function, and you may not even guess it, right? So you may not be aware, but there can exist more than one solution, one minimal expression for a given function, which you may not know. So these are the problems with this Boolean algebra theorem, minimization using Boolean algebra theorem, and that is why we want some systematic method which can lead to minimal expression. Okay, so one of such method, as I said, is called, this is very important method, Carnot map, which is very commonly known as K-map technique. Okay. So K-map is basically a graphical method which is used to simplify logical functions. Okay. K-map provides a simple and systematic procedure for minimizing logical functions. I'll show you how to draw K-map, but before that, you must understand that K-map basically conveys all the information that a truth table contains. Okay, what is the information contained in truth table? Truth table has information about what will be the output produced by the circuit for any given combination of inputs, right? For all possible combination of input rather. Okay, so truth table tells what will be the output produced by the circuit for all different combinations of inputs. The same information is contained in the K-map also. Okay, K-map is shown in the form of squares or boxes, which we call as cells. Okay, and each cell in the K-map corresponds to a unique min term of the function. We know that every logical expression has certain number of min terms associated to it. How many min terms? It depends how many variable logical function it is. If it is a 2 variable function, there will be 2 raised to 2, that is 4 min terms, right? That's why we say 4 rows in the truth table. If it is a 3 variable function, we have 8 rows in the truth table, so 8 combinations, so we say 8 min terms. If it is a 4 variable function, there will be 16, 2 raised to 4, 16 min terms. So I said K-map contains cells inside it. It contains boxes which are called cells, and each cell corresponds to a unique min-term of a given function, which means that if it is a two-variable function, number of cells in the K-map will be 2 raised to power 2, that is 4. If it is a three-variable function, number of cells in the K-map will be 2 raised to power 3, that is 8. If it is a four-variable function, number of cells in the K-map will be 2 raised to power 4, that is 16. Let me first of all show you how to represent K-map, and then we will see how to simplify logical expressions using K-map. Okay. So as I said, if it is a two-variable function, we know that total number of min terms will be 4, right? So two-variable function will have 2 raised to power 2, which is equal to 4 cells in the K-map. Okay. A three-variable function will have 2 raised to power 3, that means 8 cells in the K-map. As I said, each cell corresponds to a unique min-term of the function, and we know that if it is a four-variable function, it will have 16 min-terms. So 2 raised to a 4 is 16, so 16 cells will be there in the K-map. Okay. Now how to represent it? So if it is a two-variable function, we are going to have 4 cells in the K-map, and we show it in this way. As I said, it is shown graphically using boxes. Okay. Each square is called a cell. Okay. So this is the K-map for two-variable function, and then we draw it like this. Each column of this K-map is labeled, and similarly each row of the K-map is labeled. Okay. So this is the K-map, structure of K-map for a two-variable function, right? Two variables. It's a structure of K-map for two-variable function. Now, if I say the two inputs or two variables of the function are A and B, the label is like this: A on one side, B on other side. Okay, which means that each row will be labeled in terms of A, and each column is labeled in terms of B. Right? We know that a single variable can take either 0 value or 1 value, right? So either this will take 0 value or 1 value. Similarly, B can either take 0 value or 1 value. Okay. Either we label it like this, rows and column like this, or you can also label it like this. Wherever there is 0, we'll write D bar. Where there is 1, we'll write D. Okay. Wherever there is 0, I'll write A. Wherever there is A bar, wherever there is 1, I'll write A. Okay. This kind of labeling is done, okay, when you have to get the expression in terms of SOP. SOP means what? Sum of product terms. This we have already done, right? Sum of product terms. So if you are trying to minimize the expression and get the expression in terms of SOP form, then labeling will be like this. Wherever there is 0, you'll write D bar. Why? Because we know that sum of product means it is going to consist of min term. And how do you form min term? While forming the min term, we say that wherever there is 0, we write represented with complement of that variable. Wherever there is 1, we represent it by the variable in its true form, right? So that's why either you can do labeling with the variable B bar B, A bar A, or you can label it like 0, 1 and 0, 1 to the two rows, right? Okay. Now, I said each cell corresponds to a unique min term, right? So let us find out which min term this cell is representing. Okay. So the first cell, to find out which min term the cell is representing, you have to look at both row label and column label together. Okay. So if you look at this first cell, what is the row label associated to it? It is A bar. What is the column label? It is B bar. Okay. If I say A is my MSB bit, MSB input, and B is LSB, you have to always look from the A. Okay. So what is the label? Label is A bar, B bar, right? A bar, B bar, or you can say 0, 0. 0, 0 corresponds to min term. A bar, B bar is a min term that corresponds to min term number 0, right? So the first cell corresponds to min term 0. Okay. Now you tell me which min term this second cell is corresponding to. This cell, the cell just next to the first cell, horizontally next to first cell.
2.
It is 0, 1, not 1, 0. It is 0, 1. I said that is from A if A is MSB, right? What I mean to say is that if A is MSB means if your truth table is like this, A, B, how many combinations you have with A, B? 0, 0, 0, 1, 1, 0, 1, 1, right? Truth table will have 4 rows, right? Each row corresponds to a unique min term. First row ka min term, if you write min term, first row min term is 0, second row is labeled as 1, third row is 2, fourth row is 3, right? Isn't it? So that is what we are trying to, associate each cell with a unique min term. Okay. Because two variable function has 4 min terms, we have 4 cells in the K map. Okay. Each of these cells correspond to a unique min term. So when it is 0, 0, it means min term 0. So 0, 0 means min term 0. Clear? 0, 1. A is 0, B is 1. Corresponds to min term 1. So A is 0 means first row. B is 1 means second column, right? You see this cell, it means this cell. Where it is overlapping 0 and 1. So this is cell number 1. Is that clear? Yeah. Now you tell me min term associated to this cell. Min term associated to this cell. It will be, you have to look at A 1, 0, right? A is 1, B is 0. A is 1, B is 0. So it is 1, 0 means min term 2. This cell is 1, 1. 1, 1 means min term 3. Am I clear to all of you? Any doubt in this? No doubt?
No,
No,
ma'am.
ma'am.
Okay, fine. So this is how we represent, the K map for a two variable function. Okay. It is not necessary that MSB has to be written here down. Okay. And LSB has to be written to this side. Okay. You can also write it in this way. You label it like this. A this side, B this side. That is also okay. Okay. So this is 0, 1, this is 0, 1. But in that case, your min term numbers will change. Okay. So this is MSB, right? A is the first input. So we have to see A, B, right? So 0, 0. So this corresponds to min term 0. 0, 1. So this one corresponds to min term 1. 1, 0. So this still corresponds to 2. And this is 1, 1. So this is 3. Am I clear?
Yes, ma'am.
If you change the label, you write A this side, B this side, your min term association will also change. Your cell association with the min term will also change, and you have to write the min terms accordingly then, right? So if MSB A is this side, so it is 0, 1, 2, 3. But if it is A is on this side, so it will be 0, 1, 2, 3. Fine? Clear? Okay. This is the structure for two variable function. Two variable function has 4 cells in the K map. Okay. Now coming to three variable function. Okay. So let us look at K map for three variable function. Sorry. K map for three variable function. So K map for three variable function. Okay. We are right now just looking at the structure of K map. Then I will show you how to minimize the expression using K map. But let us first of all be clear about how to show the K map, how to draw the K map, right? A three variable function has how many min terms? It has 2 raised to 3, 8 min terms. It means K map should have 8 cells inside it. Okay. So the K map for three variable function is shown like this. So there are total 8 cells. 1, 2, 3, 4, 5, 6, 7, 8. A three variable function has 8 min terms. Therefore, there will be 8 cells in the K map. Each cell will correspond to a unique min term of the function. Yeah. Okay. Now let's say function is ABC, has variable ABC. So if this side I have to write only one variable, right? Why I'm writing only one variable here? Because there are only 2 rows to label, right? Single variable, take 2 values, either 0 or 1. So this side I cannot write two variables, but on this side I'll write two variables, B and C, right? So BC, there are two variables. How many combinations are possible with two variables? Four combinations, right? BC can take value 0, 0 or 0, 1 or 1, 1 or 1, 0, right? So there are four combinations, four possibilities, right? Okay. So now let us find out which minterm, which cell corresponds to which minterm. Again, same concept. You have to look at the label, both row label and column label simultaneously in order to identify to which minterm it belongs to, right? So the first cell, what is the minterm? See, this is a function ABC. It means if you draw the truth table, it will be like this. There will be three columns plus one column for output, right? You remember truth table, isn't it? So how many rows? Three variable function means 8 rows, 0, 0, 0, 0, 0, 1. Like this, it will go until 1, 1, 1, right? And then depending upon which function you are representing, your output will be according to that, right? So I suppose you are able to correlate the two things, truth table and the K-map, right? Yes or no?
Yes, ma'am.
Yes, yes, ma'am.
Okay. So first cell correspond to which minterm? You have to look at, see, A, B, and C, right? You have to look at label for A, B, and C. So if you look row label, first we will look at row label. Why? Because we have to look at A first, isn't it? So row label is 0 for this first cell and column label is 0, 0. So 0, 0, 0. You see 0, 0, 0 correspond to minterm 0. So this is minterm 0. Okay. The cell next to this will have minterm. It is associated with 0. This last cell, what is the minterm for this last cell? It is 0, 1, 0. 0, 1, 0 means
2.
0, 1, 0 is binary equivalent of
2.
decimal number 2, right? So this cell corresponds to minterm 2. And this cell corresponds to minterm 0, 1, 1 is 3, right?
Yes.
Now second row, first cell of second row is associated to minterm 1, 0, 0. 1, 0, 0 means 4, minterm 4. Next one is 1, 0, 1. 1, 0, 1 means 5. Next is 1, 1, 1, which means 7. And last one is 1, 1, 0, which means 6. So you see how it is going. 0, 1, 2, 3, 4, 5, 6, 7. Right? Have you observed the pattern? When you do it several times, you'll be able to memorize it. So you will not forget. You will directly write in some places. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now, if you write A on this side, you can also label it like this. It is also possible to draw the same, 8-cell K map with A this side, B this side, and C this side. You can also label it like this. Okay. A, B on this side. Of course, two variables will come on this side because there are 4 columns to label, right? And here there are only 2 rows to label. So here only one variable will come. So 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 1. Okay. Somebody may ask why it is not following binary sequence. You see the label? Can you see the column label? Is it following binary sequence? What?
No.
Is it following binary?
Oh no.
No.
No, it is not following binary sequence. Binary sequence में तो पहले 2 आता है फिर 3 आता है ना. So 0, 0 is 0, 0, 1 is 1, 1, 1 is 3, or 1, 0 is 2, right? This is not following binary sequence. This has been done purposely actually. I'll tell you the reason in some time. Okay. Now let us identify the minterms, associated to these cells. So first cell, how will you check? You have to start with MSB, right? A, B, C. So 0, 0, 0. 0, 0, 0 is 0, right? Now I'll write the down one first. Okay. What is the min term for this second cell below the first cell? It is 0, 0, 1, right?
1.
So it is 1. Next one,
3.
0, 1, 0. So this is 2. I hope it is
2.
clear how I'm writing the min term, right? You
Yes,
have to look at the row, column label, and then row label in this case. So 0, 1, 1. So this is 0, 1, 1. It is 3. Then let me write the last one first. What is the min term for this cell? 0. Sorry. First you have to look at A, right? 1, 0, 0, which means 4. This one, it will be 1, 0, 1, which means 5. This one, A is 1, B is 1, C is 0. So 1, 1, 0 is 6. And this one, 1, 1, 1, which means 7. Right? So if you write the label, if you label it in this way, MSB starting from here, A, B, then C, your min term will be 0, 1, 2, 3, 4, 5, 6, 7. I hope it is clear. Yes?
Yes, ma'am.
Okay. Now we will look at structure for 4 variables. 4 variable function. Okay. Structure, K-map structure for 4 variable function. So 4 variable function will have how many cells in the K-map?
16.
16 cells, right? So we have to draw a K-map, which will have 16 cells inside it. Okay, this is the structure for K-map of 4 variable function. Okay, and then this side will label. So let's say I'll label it like this: A, B this side, C, D this side. Okay, so 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0, right? There are 2 variables on each side. So 2 variable can take 4 different values: 0, 0, 0, 1, 1, 1, 1, 0. So AB can take 4 different values, CD can take 4 different values. So the labels are done like this. Okay. Now let us write down the min terms corresponding to each cell. So we'll start with the first cell. How will you see the min term? You have to look at the first. We will look at row label now. Why row label? Because A is here, right? A is my MSB, as I said. In every case, I have taken A as the MSB, first input, while writing the truth table, right? So you have to start from A. A, B, C, D will see like this, okay? So first you look at the row label and then you look at the column label for the cell, okay? So A, for this first cell, row label is 0, 0 and column label is 0, 0. So 0, 0, 0, 0 means min term 0, right? Then let us write this one first. 0, 0, 0, 1 is min term 1. 0, 0, 1, 1 is min term 3. 0, 0, 1, 0. 0, 0, 1, 0 is binary equivalent of decimal number 2. So min term 2. Next row, 0, 1, 0, 0. 0, 1, 0, 0 is binary equivalent of decimal number 4. So this is min term 4. 0, 1, 0, 1. 1, 0, 1. You know it is 5, right? 0, 1, 1. 1, 1 means 7. 0, 1, 1, 0. 1, 1, 0 is 6. Okay. Now let us first write the min term for last row. For last row, the first cell of last row is associated with which min term? What is the min term for this cell?
8.
8. 1, 0, 0, 0. So it is 8. Next one, 1, 0, 0, 1. So it
9.
is 9. 1, 0, 1, 1 is 11.
11.
1, 0, 1, 0 is 10. Now coming to the upper one. 1, 1, 0, 0
12.
is 12. 1, 1, 0, 1 is 13. 1, 1, 1, 1, 4, 1 is 15. 1, 1, 1, 0 is 14. Okay. So if you label it A, B this side, C, D this side, your min terms will be like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that clear? So if you make mistake in writing min term in the cell, your whole question, your whole problem will go wrong. Right? So this is very important. You must understand how to associate cell with the min term. Okay. Same four variable function, K-map, can also be drawn like this. And let me write label this time, AB on this side and CD on this side. You may write AB on this side and you can use CD to label the rows, right? So if you choose to write labels like this, now your minterm numbers will change, right? So now you tell me what will be the minterm associated to first cell. It will be 0, 0, 0, 0. This is 0. But now minterm 1 is which cell? Minterm 1 will be the cell just below the cell 0, right? This is minterm 1. Why? Because 0, 0, 0, 1. We are starting with A. So AB is 0, 0, CD is 0, 1. 0, 0, 0, 1 is minterm 1, right? 0, 0, 1, 1 is 3. 0, 0, 1, 0 is 2. Second column, 0, 1, 0, 0. 0, 1, 0, 0 is 4, right? 0, 1, 0, 1 is 5. 0, 1, 1 is 7. 0, 1, 1, 0 is 6. And if you look at the last column, it is 1, 0, 0, 0, which means 8. 1, 0, 0, 1 means 9. 1, 0, 1, 1 means 11. 1, 0, 1, 0 means 10. 1, 1, 0, 0 is 12. 1, 1, 0, 1 is 13. 4 ones is 15. And 1, 1, 1, 0 is 14. I hope it is clear. Structure of K-map structure of 4 variable function.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So now you are clear about how to draw the K-map, right? The structure is clear. Okay. Now, another important thing before I show you how to minimize the expression using K-map, one more important thing to know is that what to write inside the cell. Okay, we haven't filled the cell. We have just given the label, minterm label to each cell of the K-map, right? We have to fill this K-map. Okay. As I said, K-map contain all the information that is being carried by truth table, right? Truth table tells you what is the output for any combination of inputs, right? Similarly, by looking at K-map, you can say what is the output for this combination of input or for any combination of inputs, right? So let us fill this K-map. We haven't filled the K-map yet. Okay. So how to fill? What will come inside the cell? Right now, all the cells are blank. They are empty, right? These are just the numbers which I have written at the left, at the top corner, right, of each cell. Okay. These are just the cell numbers, right? We have to fill this K-map now. Now, what will be filled? What will come inside the K-map is either 0 or 1. Okay. Now, K-map, the value of the K-map, how do you fill the value of K-map? K-map is filled with the output of the function. Okay. So you have to refer to the truth table. You have to see what is the output given by the circuit for a particular combination of inputs. Okay. And accordingly, we fill the K-map. Okay. As an example, let's say I'll take in small simple example. Let's say a 3 variable function. Okay. You know this is the K-map for 3 variable function, right? K-map is already have. This is the K-map. Okay. Now let's say I have a K-map which says 1, right? 3 variable K-map means it will have 8 rows, right? 2 raised to 3 rows, that means 8 rows. So there are 8 minterms. Each combination corresponds to a unique minterm, you know that, right? And let's say output is something like this: 0, 1, 0, 1, 0, 1, 1, 1. Okay, let's say this is the output of this function. Okay, let's say a function is defined with this truth table. Okay, so now the K-map corresponding to this truth table will be, first of all, this will be the structure for K-map, a 3 variable K-map has 8 cells corresponding to 8 min terms. We know that this first row corresponds to min term 0, second row is min term 1, third row is min term 2, min term 4, then min term 5, 6, 7. 0, 1, 2, I missed 3, right? 0, 1, 2, 3, 4, 5, 6, 7, right? So what we fill inside the K-map is the output value of the function. Okay. So min term 0, what is the output corresponding to min term 0? Output is 0, so we'll write 0. What is the output corresponding to min term 1? It is 1, so we'll write 1 in the cell number 1. Output value for min corresponding to min term 2 for input combination 0, 1, 0. That means corresponding to min term 2, output is 0. So in the 2 cell, we'll put 0. Output corresponding to min term 3 is 1. So the output corresponding to min term 4 is 0. So we'll put 0. Output corresponding to min term 5 is 1. Output for 6 is 1. Output corresponding to min term 1. Okay. So this is how we fill the K-map. Okay. Now the K-map is complete. Okay. Now the K-map is complete and we have to see how to reduce the function, how to reduce, minimize this function. Right. Is this much clear to all of you? So what is written? What is the value inside the K-map cell? It is the output of that function. Okay. So you have to write output corresponding to that min term in the cells of the K-map. Okay. Fine. So we have seen the representation of logic function on K-map. And now we have to use grouping technique to simplify the logic function. Okay. Basically, K-map reduction is based on grouping technique. Grouping means we basically use combining theorem. Okay. So the basis for K-map reduction is the combining theorem. I hope you all remember combining.
Lecture over.
I have said na कि 2 hours का होगा lecture 1, 2, 3. You remember I had posted this.
Ma'am, we have IBM.
अच्छा पर IBM तो 3:30 के बाद होता है ना, अभी कहाँ होता है? You have IBM after 3:30, right? That is why I scheduled this lecture.
That is done at 5:30. Can we get a small break in between?
That is okay. If you want break, I don't mind. You want break now or you want me to leave you early? Continue now and leave you early?
Leave early. Leave early.
So shall I continue now?
Yes, ma'am.
We are up to from 8 in the morning, ma'am.
So I'm okay with anything. If you want break now, I'll give you break for 10-15 minutes and then we'll continue. Or if you want me to continue now, then I'll leave you early.
Ma'am, please leave us by 2:45 now.
Yeah, I'm okay with that. So I'll leave you by 2:45.
Ma'am, leave us by 2:30 now.
2:30? Okay, fine. चलो देखते हैं 2:30 तक. Remind me, okay? Fine. Now let us look at this how to reduce the logic function using K-map. Okay. So the basis for K-map reduction is the combining theorem. If you remember combining theorem, what does it say? It says, I'll write in terms of xy. Say, it says x dot y plus x dot y bar is what? Is x, right? This is what is combining theorem. Remember, right? How you got this? You take x common. So if you take x common, you get y plus y bar, which means x dot 1, which is equal to x. Okay? So this is what is combining theorem. Okay. What it means is that if you have two product terms, okay, there's a logical sum between two product terms, and the two product terms is in such a way that you see, if you see here, there is a variable. Okay, there are variables x and y, and in the second term you have this variable and complement of second variable, right? So if you have something like this, this x will be common, right? So therefore we can directly write this as x. We can replace this by x. So we are actually combining the two terms and we are getting a single term. Okay, that's why it's called combining theorem. Okay, so if you have an expression something like this, you can combine them. Okay, and you can write as a single literal. Okay. So you have two product terms which has been reduced into a single product term. Okay. So we are reducing the expression using combining. So this is the basis for K-map. In K-map, we are exactly doing the same thing. Okay. You see what you have seen here? Only one variable is changing. If I write it in terms of 0, 1, okay, so it is 0. This was 0, 0, and second term was 0, 1, right? If x and y I say 0, 0, this is 0, 1. So if you compare these two, only one literal is changing its value, isn't it? This is changing its value, so what you get is 0. This is what I mean to say. Okay, so the one which is changing the value, you simply ignore it and you write it as 0. Okay. So this is the basic, basis behind K-map reduction. If you look at K-map cell, let me just go back to structure of K-map. You see here, if you compare any two adjacent cells of K-map, okay, you compare any two adjacent cell of K-map. Let's say I'll take example of three variable K-map. It becomes more easy to understand. 3 variable K-map. You take any two adjacent cell. Let's say cell number 0 and cell number 1. How many variables are changing? Cell number 0 is what? 0, 0, 0. Cell number 1 is what? 0, 1, 0. Right? So here you see two variables are fixed. Two variables are same. Only one variable is changing. So you can simply remove this variable. Okay? And you can combine the two terms together. What I mean to say is that, let's say, let me take an example. Let's say you have these two, one present in these two cells. Okay. Now, what is this cell correspond to? What is the min term corresponding to this cell? Min term corresponding to this cell is 2, right? 2 means what? A bar, B, C bar, right? 0, 1, 0. This cell is min term 6. This cell corresponds to min term 6, which means A, B, 1, 1, 0, right? A, B, C bar. Can we apply combining theorem? Yes, we can apply combining theorem. You see, it is in this form. This is X, this is Y. This is X bar, and this is Y. You see, X dot Y, X plus X bar dot Y. So what you will get? You will get Y, isn't it? If you simplify this expression, forget about K-map. If the expression is given like this, A bar B C bar plus A B C bar. Okay. You can apply combining theorem here, right? So what you will get? Or you take it like this. A bar plus B will be left. You have B dot C bar common, right? Okay. Write it properly. B dot C bar, right? So what you get? You get B dot C bar. You get B dot C bar. So two terms, we had two terms which have been reduced to single term only now. Okay. So if you apply Boolean algebra theorem, you get this. Same thing I'm going to do
A
using
plus
K-map.
A bar.
Ma'am,
It's A plus
A
A
plus
bar.
A bar
Sorry,
आएगा.
I wrote B. Sorry. This is A plus A bar is 1. So that's why B dot C bar, right? Same thing we are doing here. You see, this cell and this cell. If you see there, only one variable is changing. Okay. Rest two cells are same. Rest two variables are same. Only one variable is changing. You compare the two min terms. Only one variable is changing. Okay. What is that variable which is changing? A, right? Here it is A is 0. Here A is 1. Here B is 1. B is here also 1. C is 1. C is 0. For this also C is 0. Isn't it? So B and C, value of B and C is same for cell number 2 and 6. What is different? Value of A, right? So only A is differing. So we can combine these two cells together and remove A. So what I am saying is that we can